process, right? For each switch we have defined step 1, right, step 2, step 3, and so on. So each for line voltages, you can see VAO, VBO, VCO, that are the phase voltages, and we derive the line voltages with the help of these phase voltages. Right? So if these VAO, VBO, and VCO are the line voltages, phase voltages, how do we achieve the line voltages? How do we achieve this line voltages? Any idea how do we achieve the line voltages? So line voltages, it's nothing but if you are trying to calculate VAB, right? So if it is a VAB, how do we calculate what we can say, a VAB? So VAO minus VBO, that will give you the third particular, line voltages. Now, second line voltage, VBC, how do we calculate VBC? VBO minus VCO. That is the line voltage for second line voltage. Third line voltage, VCA. So VCA is nothing but VCO minus VAO. That is the third line voltage. Correct? This way, we have 3 particular line voltages which we have calculated. Now, let's talk about the fourth one. Not fourth one, to draw this waveform. So these voltages, VAO and VBO, they have been subtracted to calculate VAB. So you find we have VAB for first section or first step, that is VS. For second step, we have VS again. Third step, we have this 0. For fourth step, we have minus VS and 0, so on. So for first step, we have drawn a constant value because the input voltage is constant. For second step, we have this 120 degree. Third step, 180 degree, 300, 360, like that. Now, this way we have drawn the line voltages. So we compared these line voltages and phase voltages. So VAO is the phase voltage. You can see the phase voltage is more closer to the sine wave. Though we are firing these switches in a 180 degree time interval, but still it is quite, there is difference. This is more closer to sine wave as the peak of this is there. However, if you see, I don't know what is happening. If you look into the line voltages, we have VAB, VBC, and VCA. So in line voltages, these line voltages, they are staying at 0 for some time, right? And then we have peak magnitude of VS. So this way we can observe. So it is observed that this voltage is not very much closer to sine wave, as discontinuous mode of operations we are realizing in this case, right? Discontinuous mode of operation. So if it is discontinuous mode of operation, it has a peak voltage and going 0, and then it is staying in 0 for 60 degree time interval and then increasing in the negative half. So it has the positive and negative sectors or whatever you can say, but the problem is this voltage is staying at 0 for some time. So the total harmonic distortion, THD or harmonics, we can say, are more in case of line voltage, in case of 180 degree mode of operation in line voltage. However, the harmonics are less in case of line voltages. Right. So one more important I wanted to discuss here that would really help. So we had seen the 180 degree, 120 degree mode of 180 degree mode of conduction, and similarly I have told you if you wanted to go for the 120 degree mode of conduction, what we will do. Any idea? Any idea? What is happening in case of 120 degree mode of conduction? We have to have these switches. So one from the upper leg, and that question has been asked from somebody. Like we have S1 and S2. If S1 is switched on, at least one switch from the lower leg must be on. And remember, if S1 is on, S4 we don't have option to switch on S4. So either we can go for S6 or we can go with S2. So if S6 is on, we'll get the voltage VAB. If S2 is on, S1 and S2 are on, then we'll get the voltage VAC. So that kind of operation we can get from this voltage. Right? If you go with the 120-degree mode of conduction, so we will find some non-conducting zone. It will be there. For this, you will not find any non-conducting zone, right? So, but in case of 120-degree mode of conduction, you will find out the non-conducting zone where some of the switches they are not conducting, and none of the switches they are conducting. So only 2 switches you will find out they are conducting at a time. So remember, both the switches, they cannot be the upper switch, right? One from the upper leg and one from the lower leg, they are conducting, so that circuit can be completed. For simplicity, we can take a first switch and then current can go back from the lower leg. That's all. That is the main idea behind having these switches. Now, so you have seen 2 types of inverter. One is a square wave inverter, so it is providing a square wave shape. As you can see, in case of household application, we have one domestic inverter, UPS or this. So that is the single phase inverter, and there are 2 types of basic inverter. One is known as, basically we are categorizing these inverter based on their control. So one could be the square wave, right? This is not working. Let me see my pad. Yes, it is working now. You can see we are having 2 types of inverter. One is sine wave inverter, and another one is, what is the another one?
Square wave.
Square wave. Right. Square wave inverter. Let me reconnect it. I don't know what happened. So one is sine wave inverter, and the second one is square wave inverter. What is the difference between these 2 inverters? Suppose if I am saying in charging application, I will use this square wave inverter. Can I use?
Yes, sir.
Square wave inverter.
Yes, sir. Yes, sir. I can.
The disadvantage if I am going for a square wave inverter. Any idea? If you are going with the square wave inverter, what will be the disadvantage?
You will have more harmonics in your output.
Right? It means, what is the shape of the voltage across AB terminal? So suppose if I'm talking about the single phase inverter, in this fashion, we have this IGBT, and the second IGBT, 2 legs we are, suppose we are talking about the single phase inverter. So 2 legs are there, H bridge, and then we have 4 switches. This switch is known as IGBT, right? So we have A and B terminal. Now, at the input side, we have connected VDC. So S1, S2, S3, S4. These are the 4 switching which are there. Now, if you have these 4 switches, I'm going to fire this S1 and S2 at the same time, and S3 and S4 for another switching cycles. So if you talk about this VAB, means the voltage across this VAB, that is square in shape. VAB, that is square in shape. If you talk about sinusoidal sine wave inverter, this VAB is more close to sine wave. But remember, what we have to do, we have to use some filter at the output side. Some LC filter, RC filter, whatever the filter you can see, that filter we have to use in this configuration. Right? So what would be the challenge in case, how do we get this sine wave inverter? Any idea? How do we get this sine wave inverter?
Using capacitor.
Using capacitor.
And inductor too, sir.
Inductor 2.
Using LC circuit, sir.
LC circuit, right? So output side, what we have to do, we have to use, people are using various configuration. People are using L, C, L, right? In this configuration, or only you can use the combination of L and C. So that they can make the VAB sinusoid. So that they can make this VAB sinusoid. Are you able to follow? So this VAB is sinusoidal in that case. Now, so only difference is,
Hello.
yes.
Sir, here is the question. If we will connect from square wave to sine wave inverter, we will convert the inverter from square wave to sine wave. If we will connect coil and capacitor, it can be convert from the square wave to sine wave?
Yes, but that's why I'm telling you. If you are generating square wave and if you are generating a PWM kind of waveform, I hope you people are aware about pulse width modulation scheme.
Yes, sir.
Right? So if I'm saying you are generating this kind of waveform, right? This type of voltage at the output as a VAB, and you are generating this kind of waveform. So which one is difficult to filter out? If I'm saying the first one and second one, which one is difficult to filter out? Which one is difficult? Obviously, this is square wave. That's why people are going for, because here you can see we have n number of switching cycle here, and they are going from 0 to maximum value to 0, and then again from 0 to maximum value. But here you will not find any 0 value, right? They are staying in the maximum. So filtering of this waveform, it will not be able to done by using a passive filter. We need some active filters which require to filter out this waveform. So that's why if you have a square wave, you will not be able to filter out, and you in a square wave inverter. That's why people are going with the pulse width modulation based schemes in case of sine wave. Are you able to follow? So my question is, how do we generate this type of waveform, right? How do we generate this type of waveform? That is the main question. From your controller or from DSP controller, what you can do, you can generate a square wave as well as you can generate this switching signals. But if you don't have this kind of facility, suppose I'm operating the converter in open loop and I have provided the square this pulse to the square pulses to this switches, then the output will also be this one. So we have to change the strategy which we are using to control this inverter. Now let's talk about that strategy, what we are doing so that we can produce the PWM signal, right? PWM. So if we talk about this type of system, let's suppose we have connected some RL circuit in this inverter, right? Some RL load we have connected, R and L load between these two terminals. So now we want AC output across this RL load and this VAB. So VAB is AC in nature, number one, AC output, and having a fundamental component. Try to understand. Fundamental 50 Hertz voltage, right? So if you want 50 Hertz component across this RL, you have to change the switching pattern. You don't have option. You cannot use this type of switching signals. You have provided just a square wave to this S1. No, we have to have various part of these square wave, right? Switch must be on and off in this particular 100 times. The switch must be on and off to get the sine wave, right? So we need to modulate this type of switching pattern. We cannot say same switching pattern which we are using for square wave that will happen. So how do we modulate this switching pattern? Any idea? How do we modulate it?
Modulator through carrier frequency.
Right. So what we have for this, we have carrier wave, right? Carrier wave means triangular wave. So what you can do, you can generate two signals. One is duty cycle or sine wave, which is having a unity magnitude with 50 Hertz frequency. And remember, the other signal, modulating signal may have 50 Hertz frequency, but the carrier wave which you are generating, right? After filtering, we would like to have the sine PWM, right? So we have to generate the sine, modulating wave must be the sine wave. So these two can be compared. Now, the important question, the frequency of this, the frequency of triangular wave, that is higher than the modulating wave, right? So how much higher it should be? So the carrier wave frequency must be higher than minimum 20 times of fundamental frequency. What is fundamental frequency?
Reference frequency.
Right? 20 times of fundamental frequency. Suppose fundamental frequency, if it is 50 Hertz, what is the actual frequency? 15 to 20, so that would be 1 kilohertz. 1 kilohertz. Right? So minimum 1 kilohertz frequency we have to choose for this carrier wave. It is not mandatory you have to choose 1 kilohertz. You can go with the, suppose 50 Hertz signal is there, you can choose 40 times, right? So what if I'm choosing 40 times, what would be the frequency? 2000 Hertz, if I'm not wrong, right? Yeah.
If actually frequency, suppose 1 kilohertz, then reference frequency how much?
Which reference frequency? Reference frequency means I'm talking about the sine wave which I have generated, modulating wave. Modulating wave frequency will be 50 Hertz only, right? modulating wave, I'll tell you in modulating wave, how do we go with the 50 hertz frequency. So modulating wave frequency, you have to keep in mind, it will be 50 hertz. So once you got the modulating wave frequency and carrier frequency, what do you have to do? We have to compare modulating wave frequency with the carrier wave. Right? So if modulating wave it is coming as a, let's suppose, sine wave, right? And the sine wave can be compared with the triangular one. Suppose this is sine wave, right? So what we can do, we can take a reference signal of a 50 hertz, and this is the carrier wave frequency of 2 kilohertz, 10 kilohertz, whatever you can consider, and that would be the PWM signal. So normally, if you talk about IGBT and MOSFET, right? MOSFET. So the carrier wave frequency people are choosing. Carrier wave frequency, it is the order of 20 kilohertz, or in case of 50 kilohertz, or in case of this MOSFET, we can go with the higher than this. We can go in the megahertz, even in the megahertz range. Now the question is, how do we get this VAB? So if I compare these two signals, suppose we have first this one, right? And then we can, I think it would be this much. So the second one would be this one, right? I have taken much, on this one. Now, so this is the modulating wave, correct? This is modulating wave. Now you have to choose the carrier one, right? So let's suppose the carrier, it is varying. So this one is +1, and let's suppose this is -1. Right? Modulating wave, as I told you, it will have a unity magnitude. Now let's talk about the triangular one. Now the triangular will be varying. So how do we vary the triangular wave? So triangular one, it is starting from, let's suppose, -1, right? And it is going up. Okay, so frequency is higher. So when this is completing one cycle, multiple times this triangular wave, it is intersecting the half positive cycle. So like triangular wave, we are going in this way, right? And then it is going up, down, like this. Multiple cycle it is going to complete. I hope it is clear, right? So multiple waveform that going to be completed. Now, as you have seen, we have modulating wave which is compared with the, and we have generated we have compared with the triangular wave of 10 kilohertz frequency, suppose, or 1 kilohertz, 2 kilohertz, whatever you have considered. If we are comparing both these signals, when the switch will be on, suppose we are talking about PWM A. So if we are talking about the PWM A, so PWM signal is going here, and the PWM A bar, right? It will go to the S3. What do you mean by PWM A bar? What do you mean by PWM A bar? Because it is representing the
Pulse width modulation
phase A. Yes. So means if the upper leg is on, S3 will be off. So PWM A, if it is 1, it will get 0. If it is 0, if it is 1, this will be 0. Correct? So PWM A and PWM A bar, that are opposite to each other. Correct? So let me draw the PWM A. How do we draw this PWM A? PWM A. So in this point we have to take. So I hope you understood the concept here. PWM A means whenever this signal, modulating signal, is higher than the triangular wave, then only the waveform will be generated or the switch will be on. So we have to see. So in this common point, what are the intersecting points that we can draw here? So these are the intersection points, right? Where these modulating wave and this waveform, they are intersecting. This is the intersection point. This is the intersection point. This is the intersection point. And then this is the intersection point. we will draw all the intersection point here. The intersection point, this is 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 the intersection point, and this is the intersection point. So what I told you, this switch will be on when the modulating wave is higher than the triangular wave. So here the modulating wave till this point it is negative, and after this it has become positive, and it become more than the modulating wave. So triangular wave is smaller or it is lower than the modulating one. So switch will be on for this. So this is PWM A. Now for this section, the triangular is higher, so switch will be off. Now in this section, modulating wave is higher as the triangular is negative, so it will be on. For this, triangular is higher, so it will be off. Now in this case, the modulating wave is higher, however this triangular wave is negative, so it will be on. Here triangular wave is higher, so off. Here the modulating wave is higher, so it is off. Here it is, off and on. Then modulating wave is lower than this, so off, on, right? It will be on in this case, no, here higher, here, and this one is correct. And then triangular is higher here, this is higher, higher, and so on. So this way we are going to see what are the kind of pulses which we have generated for PWM A. Now if I'm saying draw the PWM A bar, can you draw the PWM A bar? Can you draw the PWM A bar? Can you draw this PWM A bar? Anyone?
Sir, downside.
Downside?
Negative.
Negative. Why negative? It is not negative. But we are saying if switch 1 is on means when the switch PWM A is on, PWM A bar, that the lower switch will be off, not negative. So what does it mean? If we extend this waveform here, right, these dots here, it means if the switch is on, right, if the switch is PWM A is on, so this switch will be off. What about this? This is off, so this will be on. This is off, this will be on, right? This is on, so this PWM A bar means it is off. So the in the space where this switch is off, PWM A bar will switch on the lower leg. That's all. So that's through or there must not be any mismatch between the PWM A and PWM A bar. So the lower leg, because we cannot switch on both the switches at the same time, right? A and B or whatever the A and A bar. So because otherwise this DC bus will be shorted. DC bus will be shorted. So that we have to take care. Now it is off, it is on, off, like this. So this is the PWM signal for this S3. Correct? So S1 is on, S3 is off. And we have drawn the voltage for VA. This for branch or the phase A we have decided. Now for phase B, so phase A at positive potential and phase B is at negative potential. Means if we are drawing the phase sequence for A in this manner, like this, so phase sequence B will be opposite because it is a negative terminal. So phase sequence B will start from the negative and then it will reach to the positive. Correct? So if we want to draw this PWM B, how do we draw this PWM B? How do we draw this PWM-B? For PWM-B, you have to draw one more, waveform, right? So if phase A is modulating wave in this way, the phase B modulating wave will be somewhere like this. Somewhere like this. So this is representing the phase B modulating signal. Phase B modulating signal. And this is representing the phase A modulating signal. Phase modulating signal.
Are they 180 degree apart? Those?
Yes. At potential A and B, you can compare. No? This is positive, this is at negative potential. Correct? So this will be the potential at A that is 180 degree phase shifted from potential B. So if we are taking the intersection again and following the same pattern, so let's draw the signal for this intersecting points for this waveform. Let me take a different color. No, it's okay. We can compare the both modulating signal and Compare both modulating signal and triangular wave signal. Modulating signals and triangular wave signals. So when this will be on? So in this, till this point, so modulating signal is higher than the triangular one, so it will be on. PWM-B is on. Now in this section, the triangular wave is on. Triangular wave is higher than this, so it will be off. In this section, the triangular is lower than the modulating signal, so it will be on, off, right? And then on, off, and then it would be on, and then it would be off for this time period, and this would be on, right? Off, and no, in this section, yes, it would be off, we can say, and then in this section it would be on, and then off, on, off, and then on. Okay? So this way we have PWM-B. Now, can you draw the PWM-B bar for lower switch? PWM-B bar. Draw the PWM-B bar.
The off position is on. PWM-B off position is a PWM-B bar on position.
PWM-B for switch 1. PWM-B bar for switch S3.
S3.
Just hold on.
Excuse me. Hello.